arcs and chords of circles, angles and sines of angles. This is a quote from Sri Bharati Krishna Tirthaji's book, Vedic Mathematics, and it comes from this page here, page 362, and these are the relevant items. Arcs and chords of circles, angles and sines of angles, etc. The converse, i.e. sines of angles, the angles themselves, chords and arcs of circles. We can get some idea what Tirthaji was referring to here, because he doesn't give us any more information, from a diary in which he wrote. You can see the title here is chord of a circle equals value of sine alpha, which is the title of this page here. And this section of Sanskrit, which is expanded into this formula here, comes from the Lilavati of Bhaskara, verse 219. The formula which Bhaskara gives is then written like this by Tirthaji, and from this we can see that the diagram must be like this, in which the radius of the circle is a half, and alpha is the angle that subtends half of the chord. Tirthaji then expresses this formula here, and this is the one we're interested in here. So this is the equation he's written. So let's take a look at it. It looks quite complicated, but it's not as difficult as you might think, because pi over 2 squared, which appears in two places, is a standard value which could be memorized. And pi over 2 can also be memorized. So if we want to find, say, sine of 0.4, we put alpha equal to 0.4, and we get this. So this is pi over 2 squared, here and here. This is pi over 2, and there's your minus 0.4. And you'll see that the value of this, when it's calculated, pi over 2 minus 0.4 squared, appears in the denominator, and a quarter of it is added to the pi over 2 squared. So there's a bit of work involved, but it can be worked out with the Vedic techniques. We can simplify this, though, by considering the cosine, because cosine is 90 minus sine, and that means that this formula leads to this one. And this is a little easier to work with. In fact, we can multiply the top and bottom of this fraction by 4 to get this equation. And then if we want to find, say, the cosine of 0.4, it's fairly easy. Pi squared, again, we can commit that to memory, 9.870, minus alpha squared times 4, which is 0.64, alpha is 0.4, and the alpha squared appears in the denominator. So we can work that one out and get the answer for that. Now let's look at degrees. These are the two formulas we've got for sine alpha and cos alpha. And if we replace pi over 2 with 90, because pi over 2 radians is 90 degrees, we get this for sine alpha, and we get this for cos alpha. And this is the formula I'd like to draw your attention to, because it's quite a simple one and it's very easy to apply. So cos 40, for example, simply means putting alpha equal to 40 here. So it's 8100 minus 40 squared over 8100 plus a quarter of 40 squared, which is 400. That's easily reduced to 13 over 17, which with Vedic mathematics is very easy to evaluate. We can use the method for recurring decimals or straight division. If you wanted sec 40, it's just 1 over cos 40, so it would be the same calculation as here, but the fraction we get will be upside down, so it's 17 over 13, which again is easy to work out. And if we want sine, well, that's okay, we can get sine from this formula as well, because the sine of an angle is the cosine of the complementary angle. So sine 70 is just cos 20, where 20 is 90 minus 70. So we put 20 in our formula and we work that out and we get the answer. So this is a nice formula and it's fairly accurate too. And surprisingly, it has zero error at 3 values of alpha. 0 degrees, 60 degrees and 90 degrees. So the error is 0 3 times in the range 0 to 90. Inverse functions, if we take that formula again for cos alpha, we can rearrange it to get alpha as a subject, and we get this, which we can use for finding inverse cosine and inverse sine. It does involve a square root. There may be a better way. It's explained in my paper. Inverse cosine of 0.2, we put cos alpha equal to 0.2 in here, and we get this, which means we have to find 16 over 21 and take a square root and multiply by 90. And this is accurate to 1/10 of a degree. And for inverse sine, well, if we want the inverse sine of 0.2, we can work out the inverse cosine and take it away from 90. It's just 90 minus the last answer, 11.44 degrees. So let's have a closer look at this formula of Bhaskara's. This is the equation here, and there it is written out. We can rearrange it like this. It's fairly straightforward to rearrange it, and we've got all the straight lines on one side and all the curves on the other side. And it turns out that this product here of these two fractions is quite close to sine alpha. And if we were to rearrange this further, so that this chord here is the subject, which is going to be equal to sine alpha, then we get the 4 plus the chord over here and the 5 underneath, and we get this equation. So as I said, the product of these two fractions here, this is explained more fully in my paper. The product of these two fractions is quite close to sine alpha, and this multiplying factor here increases the accuracy to make it very accurate. So this is an interesting process that Bhaskara has come up with to find such a nice approximation to sine alpha. So we could apply that method to, say, finding a formula for tangent. So this is the equation we just had, in which the product of these two fractions gives you an approximation to sine alpha, and this factor here increases the accuracy. So suppose we start off with alpha over 90 minus alpha as an approximation to tan alpha, where alpha is in degrees. We'll find that the curve there does have similar properties to the tan alpha curve, just as this product here of these two fractions has similar properties to the sine alpha curve. And we can apply a multiplying factor to make it more accurate, this one here, which simplifies to this. So this is a formula we can derive for tan alpha following the same sort of scheme as Bhaskara used for sine alpha. So here we've seen that Bhaskara's formula leads to another formula which can be modified to deal with cosines and to work with degrees. And it can also be reversed to give a formula for inverse sines and inverse cosines. And we've seen that the original formula may originate from a two-stage process which can be applied to other functions like tangent and other trig functions and exponential and logarithmic functions. Thank you.